Welcome to this special program by Université de Montreal in collaboration with the Rio Tinto Alcan Planetarium. After delays and extensive testing, the James Webb Space Telescope is finally ready to launch on December 18 or within the following days aboard an Ariane 5 rocket in French Guiana. It will succeed Hubble, which was launched in 1990 and has made remarkable astronomical discoveries. It will then become, James Webb will be the largest telescope ever deployed in space. So this is not a small event. This is not something that we see every day, right? So in order to learn more about this new tool, in order to better understand how it will most definitely change the way we see and study space, we brought together a very own panel of experts, starting with René Doyon. You are a professor in the Department of Physics at Université de Montreal. You're also the director of iREx. We also have Nathalie Ouellette. So you are an astrophysicist. You're also an iREx collaborator. And we have also Olivier Hernandez, so director of the Rio Tinto Planetarium. We also have you as an astrophysicist, and you are the co-founder of iREx as well. So thank you all for being here. It is pretty rare to have you all on the same panel, I believe. Yeah. So we're very lucky, and we're talking about the most complex machine ever created by man. So we're going to jump right into it. I'd like to know first about the genesis of Webb. So how did it all start?
Well, it all started after the launch of Hubble in the mid-90s, and astronomers were already thinking of the next telescope that one could build. And at that time, we were talking about a 4-meter telescope operating at infrared wavelength, as opposed to visible wavelength for Hubble. But it's really the ninth NASA administrator, Dan Golden, that really kicked this project. And one day, he was in front of American astronomers, and he really said, "You guys should be more bold. You should build a 6-7 meter telescope." And he got a standing ovation. And
oh yeah, we're always looking for more, right?
Yeah, well, but that's pretty rare. From that, usually, you know, people say, "No, a little smaller." Or
there's a lot of downscoping, typically. Yeah.
Exactly. So at that time, it was an 8-meter telescope. We're now in about 2000. It was called the Next Generation Space Telescope.
Wow. And how? So what will Webb be used for specifically?
So there are lots of different missions. We put them in 4 categories typically. So it's going to look at alien worlds or other worlds in our solar system, but also exoplanets beyond, which is iREX's specialty. Also looking at the stellar life cycle from the birth of stars all through their lifetime until they die and become white dwarfs or neutron stars or black holes. Also studying galaxies through time, galaxies which are a personal favorite of mine, and really pushing to the very first galaxies that were ever created about 200 million years after the Big Bang, and being able to see really the early universe, farther even than Hubble was able to see.
And this is something we've never done before.
No,
right?
So we're really pushing the envelope. We're taking what Hubble did, we're building on that, and we're going to go even further.
Olivier, maybe tell us how, so we're talking about Hubble, how is it different? How is Webb different? How is it better?
It's better because it's larger.
Okay.
So
it's the size, really?
The size of
bigger is better.
Bigger is better.
For telescopes.
So the diameter of the telescopes is around 6.5 meter instead of 2.4 meter for the Hubble Space Telescope. So it's a better telescope because it's a larger one, but also because it has been designed to study the infrared light, which is what not typically the case for the Hubble Space Telescopes. And so it will give us some clues for the past of the universe, and also for the sign of life elsewhere that the telescope spatial Hubble was not able to do that. So this is the main differences between the 2 telescopes.
Okay, so we're talking about infrared.
Yeah.
Compared to the current technology we have with Hubble, how is it so different, and what does it allow more?
Well, Hubble was really designed to operate at visible light, but then with time we upgraded its instrument to operate a little bit in infrared, but it's really not optimized for doing this. And just to pick up on Nathalie's goal to find the very first galaxy, we have to understand that the very first galaxy, they are very bright at ultraviolet light. But because of the expansion of the universe, that light is shifted in the visible and infrared. And in fact, Hubble is just blind. it cannot see these galaxies. So Hubble saw maybe 500 million years, but we still need 300 million years to
we need to put glasses.
Exactly. And well, we need to go to take wavelength where we can see these galaxies, and this is in the infrared.
Yeah. Another really interesting thing about infrared, the universe is a very dusty place. There's a lot of cosmic dust all over the place, and it makes for beautiful images for the Orion Nebula or the Pillars of Creation. But there's a lot of stuff hidden behind that cosmic dust, and that dust blocks out visible light, but infrared can actually punch through that light. So you're opening a whole brand new window on the universe by looking at infrared light to look what's behind this cosmic veil.
Interesting. And well, you're all connected to Université de Montréal. We know that Université de Montréal has a big part to play in the James Webb Space Telescope. So when did the university got involved, and what was its implication exactly?
Well, it all started at the international level when NASA wanted to have Canada, through the Canadian Space Agency and the European Space Agency, to be involved. And at that time, in the early days, Canada was only providing one instrument, which is the Fine Gathering Sensor, which I will talk briefly. And myself, I got invited to join an American team. At that time, we did not have our instrument, but with time, we got our own instrument. And that's how Université de Montréal got involved. And it's basically because the only people in Canada that had expertise in infrared astronomy was really in Quebec. So it's not a coincidence that this is a Québécois involved in this project. It's because infrared astronomy was born in Quebec, and more specifically at Mont-Mégantic Observatory.
And it's not just Quebec. It's also women that were involved in the projects since the beginning in the last years. I believe there were 2 women from University of Montreal, and Nathalie, I believe you're one of them. In the last 3 years, you were involved in the mission. Can you tell us a little more about that?
Yeah, definitely. So, as we know, physics and astronomy tends to be a male-dominated field, but this is changing over time. We're really trying to get that gender equity and parity inside of our field, and we're really seeing this, especially with the evolution of Webb and the project. So, I'm the outreach scientist, so I act as a sort of bridge between the scientific team and the general public to really try to make all the wonderful discoveries we're going to make accessible to the public. But we have other women and other very young women who will be leading projects in the first few years of Webb's operations. And it's really showing that the next generation of astronomers and astronomers using Webb have a different profile that matches a lot more closely the profile of the general public. So that's really fantastic to see that.
And you're talking about one young woman in particular, Olivia Lim. René, can you tell us a little more about Olivia?
Yeah, Olivia is a student of mine. She's doing a PhD on exoplanet, and we have a major program to study exoplanet atmospheres. And Olivia, and to look at this famous rock star planetary system. It's the TRAPPIST-1 system that has 7 planets the size of the Earth and the mass.
That's crazy. And
we know that 3 of them are right in the habitable zone, this region where we can hope potentially find liquid water at the surface of these planets. And Olivia wrote a proposal which was competed internationally and to observe these planets. And this is the largest program allocated to Canada.
So we're talking about exoplanets, we're talking about trying to know what's in their atmosphere. I'd like to jump to the scientific goals of the James Webb Telescope. So let's talk about iREx and how maybe it'll allow us to actually measure what's in the atmosphere.
iREx has been specifically developed and designed to study the atmosphere of exoplanets. So this is what René's team has done very precisely in order to be sure that we will be able to analyze correctly and to be able to find what we call a spectrum of an exoplanet, of the atmosphere of an exoplanet.
So it's a camera?
It's not a camera properly. It's what we call a spectrograph. It analyzes the light and try to identify the different wavelengths that are in the atmosphere of an exoplanet. Mm-hmm. So this is the main goal of the instrument, in fact. And we will not have an image of an exoplanet. We will have the signature of some elements into the atmosphere of the exoplanet. It's much more data, a graph, than a perfect image. But it's very important to have this kind of graph because it will give us the clue and the signature, the biosignature, maybe are into the atmosphere of the exoplanet.
I could add that our instrument was also designed to look also at galaxies. This is one of our main goals. We're going to be
distant galaxies.
Distant galaxies.
Yeah.
We're going to be looking at clusters of galaxies, and we'll be able to take spectra of all of them. 3,000, and we know that these clusters have dark matter, hidden mass, and Einstein taught us that light is deflected by mass, and so we use these clusters as gigantic lenses, gravitational lenses, to detect galaxies that are behind, the very first galaxy. So we hope to be able to detect these galaxies as well. So NIRISS is a very versatile instrument that can do many things, and the two main goals is, exoplanet atmospheres and distant galaxies. And another thing, on the backside of NIRISS, we have the fine guided sensor, which is not a scientific instrument, but nonetheless a mission critical. It's a camera that allows to correct the vibration that the telescope will experience whenever we observe. And so what we do, we take a star and we measure its position 16 times per second, and we send the signal to a small mirror to correct the image so that they are very, very sharp. To give you an idea of how accurate it is, the telescope, our instrument will be able to detect a movement of the telescope equivalent to the thickness of a human hair as seen as 1 kilometer. Or if you want, it's like someone in Toronto blinking at me sitting in Montreal. It is that accurate. So remember, every single discovery, every image, spectra that will come out of Webb will have been guided by the Canadian eyes.
So now, instead of having the Canada arm, like in the space station, International Space Station, we have the Canada eyes aboard the Webb telescope.
And when we want to, wanting to know what's in the atmosphere, for example, of the exoplanets in these galaxies, is wanting to know if there is life, potentially. So the big question is, will this new telescope lead to maybe the discovery of extraterrestrial life?
We don't want to say no. It's a question that we've been asking for millennia as a humanity, as a civilization. And the road to that answer will be fraught with lots of maybes and false positives, and we're not sure. We saw it with the possible detection of phosphine on Venus about a year ago now, and now we're not sure anymore. So we're hoping that, and we know that Webb will be a huge step forward in that quest. So to know that there are planets out there that have the atmosphere that is similar to what we have on Earth, that could potentially harbor life, or life could develop there, is already a really big step. And we could potentially see first possible biosignatures, but it will be important for Webb to work in concert with other telescopes, like the next generation of giant telescopes that will have 30 and 40 meter large mirrors on the Earth to confirm those signatures. So it's going to be a big collaboration between a bunch of different space telescopes and different ground-based telescopes, but Webb will certainly be a huge step in that direction.
And the key word is, as Nathalie mentioned, atmospheres. This is the next big step, be able to detect the atmospheres and also determine their chemical compositions. And the NIRISS instrument and also all others on board Webb will be capable of doing that. So it's going to be quite exciting.
Yeah, and the other keyword is collaboration, as you said.
Yes.
Because you need everybody work on the same topic to be sure that we find something. And also because we work with all the telescopes from Earth to space in order to find those kind of biosignatures.
It's a huge collaboration at all levels, local, national, and international.
You're all very excited about it.
Yes, everyone, yeah. We tend to say that about 10,000 people across the world worked on Webb over the various decades that it's been working on. So lots of people will be excited on December 18th.
Yeah, because it's 20 years of work.
It
you
is,
didn't
it's
mention
over 20
that, but
years
it's
of work, yeah.
Much more than 20 years, in fact.
So more than 20 years of work, big budget, right? Over $1 billion.
It is.
Go ahead.
It's $10 billion, but I was looking, so recently the US put out their decadal survey where they plan out the next 10 years of astronomy in the US. And Hubble, in adjusted dollars, 2021 adjusted dollars, cost about $10 billion without all of the corrections and repairs that happen after the fact. And look at everything wonderful. We don't talk about Hubble's budget. We talk about Hubble's wonderful science and pictures now. And I think Webb will be the same thing, essentially.
I mean, it's over 20 years, so.
Yeah.
For Canada, this is $180 million. So spent over 20 years, you can do the math. It's about 50 cents per taxpayer. So I think it's for it to be.
That's not so bad. Yeah.
I think it's a good deal to be part of this incredible machine.
And the launch was, so it was supposed to be in October originally, and now it is planned for December 18. It could also be in the following days, right? So why is it so hard to plan the launch date, and why is it such a small window? Can someone take this one?
Sure. For Hubble, we had a second chance. The start of Hubble was a little bit difficult. There were some aberrations in its optics, and so the first images that came out of Hubble weren't great. It needed a repair with the Canadarm, actually, 3 years later, and then it's been doing fantastic science since then. But the reason why that was possible is because Hubble is in low Earth orbit, just a few hundred kilometers above our heads. Whereas because Webb is an infrared telescope, we need to put it way far away from the Earth. 1.5 million kilometers away, that's 4 times the distance to the moon. We can't repair it if something goes wrong. So it's been very thoroughly tested, and anytime there was a minor snag, we stopped everything. We had to find the root cause of the problem and fix it. And so there are delays in that process, but it's to make sure that we've got one shot, and that shot, we make it count.
And you say, you know, things could go wrong. There could be, so what's the lifespan? What is the expected lifespan?
Webb has a minimum life mission of 5 years.
Okay,
but everything,
it's not a lot.
Yeah, but everything has been designed to last more than 10 years. And in fact, the main limiting factor is the fuel. You know, sometimes we need to do corrections on its orbit. Webb is on a very stable orbit, but sometimes we need to do some tweaks, and that is done with fuel. And we have a tank for about 10 years.
But people from engineering are very conservative, in fact.
It could
You
be
say,
longer.
yeah.
Okay.
You just look to the
We don't want to set our
Perseverance.
hopes
Yeah, the
up.
Mars rovers.
The Mars rovers, for example.
Okay.
It's, the lifespan was around 1 year.
Something like that, and it ended up.
It's 10 years now.
Yeah.
10,
Yeah,
so
and it's been proven that they can last 10 years. For example, we have a mechanism inside our instrument, which is a filter wheel. We can move optical element in and out, and it has to operate at minus 33 Celsius. It was a lot of work and design. But we built a development model that we exercise over, you know, an increment of 10 years of operations, and it was fine. Not at the beginning. We had issues and problems to solve,
Yeah, well,
but we fixed it, and it took
how
time.
science
Yeah.
works, that's right.
Once it's launched, when can we expect to see the first visuals?
So it'll take about a month for it to get to its final destination, and then a few months for it to cool down to very, very cold temperatures, about 40 degrees above zero, above absolute zero. So we should expect, and then the mirror has to be calibrated so that it's all pointing correctly. The instruments will have to be tested, so we can expect the first few images about 6 months after launch.
And René, you'll be the only one officially on site at the launch. What are you most excited about?
Oh, well, first I'll be there with colleagues from the Canadian Space Agency and also Honeywell, the company that built the instrument in Ottawa. Yeah, I mean, this is my first rocket launch I will ever see.
That's,
So
that's one thing.
yeah, I'm really excited, and I haven't been 20 years in this project. It's sort of an abstract thing, this project, right? You just get used, it takes time. But now every morning I wake up, it's okay, that's one day less before
It's
launch.
great. Yes, it's
Yeah,
coming.
I'm
It's coming.
very
And hopefully December 18, right?
Oh, I'm not worried
Hopefully.
about that.
No?
I mean, the telescope has been there for now several weeks, and everything is going smoothly. And it may be a glitch with the weather that we need to delay by maybe a few days. But we have several launch windows, and it would be surprising that we don't launch close to December 18th.
And what would be the next steps then? What's to expect maybe now until the launch and afterwards? How are you going to use the visuals? How are you going to share with the public?
we will wait for the first real images to share with the public. I think it will be 6 months later. So, of course, we will present the images into the planetarium, and we will discuss and try to talk to the people how it was difficult to do such images, because it's very abstract. So I'm pretty sure that those images will be very spectacular, and it will attract a lot of people to see those pictures. But everybody will be able to see the images on the website of the NASA or the.
So it's going to be accessible, and
it will be very accessible.
More than ever.
Yeah,
so
it will be.
Those will be images and data taken from all science instruments, and it's a big secret as to what they will observe. I don't even know myself. I propose objects that I'd like my instrument to be used, but to be honest, I don't know. I'll probably know it at the last minute.
But I'm thinking even further than that. This is the first time that Canada is part of this kind of mission. We weren't formally part of Hubble. We did some stuff with the data, and we helped on that side. But I'm just hoping that this gives the Canadian Space Agency the momentum to participate in these international collaborations and these huge space astronomy missions. And it's just the start of this kind of thing for Canada.
Yeah, well, it's very exciting. Really looking forward to it. Thank you all for sharing your knowledge. Olivier, Nathalie, René, thank you very much. And we're really looking forward to the launch on December 18th.